Let's look at some examples involving area and definite integrals. In this first problem, we're asked to find the area under y equals x squared over the interval 0 to 3. It's not necessary to graph the curve y equals x squared, but it does help give us a visualization of what we're trying to find here. So we're trying to find the shaded area over the interval 0 to 3 under the graph x squared between x squared and the x-axis. Well, we can calculate this by calculating the definite integral from 0 to 3, since that is our interval, of our function x squared with respect to x. Alright, so let's calculate this. The antiderivative of x squared is x cubed divided by 3, and then we want to evaluate this on the interval from 0 to 3. So first we're going to plug 3 in for x. So we have 3 cubed over 3. And then we're going to subtract from that what we get when we plug 0 in. So we end up having 3 cubed, which is 27. So 27 divided by 3 gives us 9, and then minus 0. So our answer then is 9. 9 is the area for this region under the curve between the x-axis and the curve, between 0 and 3. Now what we used here in this first problem was the fundamental theorem of integral calculus. And what that tells us is that if we have a continuous function, lowercase f of x, if we're interested in calculating the area of the curve, lowercase f of x, over a closed interval, say a to b, then we can find that by taking the integral from a to b of our function lowercase f of x with respect to x. And to evaluate that integral, we take the antiderivative of lowercase f of x. And we're going to let capital F represent the antiderivative. And if we evaluate that antiderivative for b and then subtract from that the antiderivative evaluated at a, that gives us our definite integral evaluated on the interval a to b. The next example here, we have find the area under y equals 1 over x over the interval 0 to 4. Now we can graph this to get an idea of what we're looking at. And the graph of y equals 1 over x looks something like this, and we're interested over the interval 1 to 4. So if 1 is here, 2, 3, 4. So over that interval, so let's say from 1 to 4, we want to find the area under that curve, under the curve and between the x-axis. Alright, so to find that, we're going to calculate a definite integral. So the integral from 1 to 4 of our function 1 over x with respect to x. So we take the antiderivative of 1 over x, which we know is the natural log of x, and we're going to evaluate that at 4 and at 1 and then take the difference. So here we have the natural log of 4 minus the natural log of 1. And we can plug this in our calculator and get a decimal approximation. We know that natural log of 1 is just 0, and then natural log of 4, if we approximate that, is approximately 1.39 rounded to 2 decimal places. In this next problem, we're asked to explain what the shaded area represents. Here we've got time in hours along the x-axis, represented by t, and we've got velocity in miles per hour along the y-axis. I'm going to label this velocity function here v of t. Alright, when we go to calculate the shaded area under a curve, between the curve and the x-axis, we calculate an integral. So we calculate an integral, a definite integral from, in this case, 0 to some time, we'll call it t. And then we take our function, v of t, we calculate the area under that. In this case, our variable is t, so with respect to t. Now let's think about what this represents. I mean, this represents the area under the curve. And this v of t here, the units for v of t is miles per hour. So we're calculating miles per hour. And what's happening is that's getting multiplied by d of t when we think about calculating an infinite number of rectangles in here, where the height is given by the velocity function and then the width of each rectangle is given by, say, d of t. Well, d of t is time, and time is in hours. Alright, what happens when we multiply these? Hours cancel and we're left with miles. That is our units. So it's kind of one way to think about here. What we're left with is miles. So this shaded area represents the total number of miles traveled. So we can say the total number of miles traveled in t hours is what the shaded area represents. In the next example, we're asked to find the area under y equals 2 minus x squared over the interval -2 to 1. Now, if you like to get a visualization of what you're doing here, then we should graph this function to see what it looks like. And what I would suggest doing, if you're interested in seeing the graph, is to use your graphing calculator to get an idea of what the graph looks like. If we plug this in the graphing calculator, we get a curve that looks something like this, and then we want to find the area under that curve over the interval -2 to 1. And it turns out that -2 and 1 are the x-intercepts. So we're interested in finding this shaded area here. Alright, so we're finding the definite integral from -2 to 1 of our function 2 minus x squared with respect to x. So we need to find the antiderivative of 2 minus x squared. So the antiderivative is going to be 2x minus an x squared over 2. Remember, we add 1 to the exponent and then divide by that, minus an x cubed over 3. And then we're going to take this antiderivative, we're going to evaluate it at 1, we're going to evaluate it at -2, and we're going to take the difference. So here, if we plug 1 into the antiderivative, we're going to have 2 times 1 minus a 1 squared over 2 minus 1 cubed over 3. And then next what we're going to do is we're going to plug a -2 into our antiderivative. So we're going to have 2 times a -2 minus a -2 squared over 2 minus a -2 cubed over 3. Alright, then when we go to simplify this, we're going to have a 2 minus 1/2. So 2 minus 1/2 is 3/2. And then minus 1/3 minus, then we're going to have a -4, and then minus -2 squared is 4. 4 over 2 is going to give us a 2. And then minus, we're going to have a -2 cubed, which is a -8/3. So a minus -8/3 is going to be a plus 8/3. Alright, and then when we go to simplify this, we have a 3/2 minus a 1/3. If we get a common denominator there so we can subtract, we're going to have a 9/6 minus 2/6. And then we have a minus, we're going to have a -6 plus 8/3. So here 9 minus 2 is going to give us a 7/6. And then we're going to have a minus, if we write a -6 with a denominator of 3, we're going to have a -18/3 plus 8/3. So here we have 7/6 minus -18 plus 8 is going to give us a -10/3. So now getting a common denominator here, common denominator would be 6. So we have 7/6 plus, having a denominator 6 would make this a 20, and we get a plus because we have 2 negatives there. So we end up with 27/6, or if we write that as a decimal, 4.5 or 4.5. Represents the area under the curve over the interval -2 to 1. In this next problem, we're asked to evaluate a definite integral. So to evaluate this, we first begin by finding the antiderivative of 4t cubed minus 1. So the antiderivative, we're going to add 1 to the exponent. So we have 4t to the 4th, and then we divide by the exponent of 4. Then we have a minus, and then the antiderivative of 1, in this case is going to be t, since our variable is t. And then we're going to evaluate that antiderivative at 2 and also at 1, and then subtract them. I'm going to simplify our antiderivative a little bit. Since the 4's cancel, we're left with a t to the 4th minus t. Alright, if I plug 2 into that, I'm going to have 2 to the 4th minus 2. And then I'm going to subtract from that quantity what I get when I plug 1 into the antiderivative. So 1 to the 4th minus 1. So here 2 to the 4th is 16. 16 minus 2 gives us a 14. And then we're going to have a minus 1 minus 1, which is 0. So our answer then is 14. Alright, in the next example, we're evaluating a definite integral from -5 to a negative e for our function x minus 1 over x with respect to x. So to find this, we're going to find the antiderivative of our function. The antiderivative of x is x squared over 2. Then we have minus, and then the antiderivative of 1 over x, remember that's one that we have to remember. The natural log of 1 over x is the natural log of x. And here we don't know whether x is positive or negative, so we have to do the natural log of absolute value of x is the antiderivative. And then we are evaluating this at a negative e and also at a -5, and then we're going to subtract. Alright, so here, plugging a negative e in, we have a negative e squared over 2 minus natural log, the absolute value of negative e. And then we're going to subtract from that what we get when we plug a -5 in. So we have a -5 squared over 2 minus the natural log of a -5. Alright, so when we simplify this, a negative e squared, when we square a -1, it becomes a +1. So this is going to look like 1/2 e squared. And then we have minus a natural log of an absolute value of a negative e. Absolute value of a negative e would make it positive e, and we know that the natural log of e is 1. So this quantity here is just a 1. So minus 1, and then we're going to have minus, when we have a -5 squared, that is 25 over 2. So we're going to have 25 over 2 minus the natural log of the absolute value of -5, so it's going to become +5. Alright, and then when we simplify this, we're going to have a 1/2 e squared, a -1, and a minus 25 over 2 is going to be a minus 27 over 2 plus, because we have a minus and a minus, so plus natural log of 5. And there we have our simplified answer for this definite integral.